So with that, now the boring stuff. So last lecture was kind of intense. There were a lot of technical moving pieces. But here I tried to summarize what is the punchline of what's going on. Okay. So we were looking at this gravitational path integral. We have the tree-level contribution and this one-loop contribution plus corrections. And we basically, the main part of the lecture was trying to understand how you compute this one-loop correction. And the bottom line was that inside of this expression, inside of this heat kernel here, there was a logarithmic contribution to the one-loop determinant. And I hope I convinced you that that contribution was basically coming from one term. So this logarithmic contribution will basically affect the entropy of the black hole. So you will get a logarithm of A times a number. And the contribution that comes from the heat kernel, which I'm going to be calling C local, is this integral of BD, where BD is basically the coefficient in the small s expansion of the heat kernel. Okay? So one thing that is important I mentioned at the end of the lecture was that from this one loop determinant, here I put, the reason why I put a little dash there, it's because what we basically focus on is the contribution when the eigenvalues are not zero. Okay? So, and that's what I'm calling C local. It's the contribution of the log that comes from the non-zero eigenvalues. You also have zero mode contributions. Those are computed separately, and they tend to just be understanding how you normalize those zero modes, and then they have very, very simple contributions to the path integral. But I won't have time to explain in too much detail how you do that computation, but we'll come back to these zero modes in a moment. Okay? So this is the expression, and then the two main, there's two main lessons to remember about this. So this thing, the C local, is basically determined, the only thing that will contribute to it, there are some assumptions about how the two-derivative theory looks like, but basically, in order for you to compute this correction to the black hole entropy, you just need to know what the low energy effective field theory is. Okay? So this is what is kind of nice about this, that I don't need to know the UV completion quantum gravity, I don't need to know the details of it. If you specify what your low energy theory is, then that fully determines this correction. Of course, there's more corrections. This is not the final answer to the entropy, but this is one contribution to the leading area. And now the other thing that maybe was not super obvious from the equations, they did not highlight it, but it's very important to mention, is that this local contribution, you can see it from this expansion. It will only appear when the number of dimensions is even. Okay? Because of this d over 2 that it's here. It's not more deep than that. So only an even number of dimensions. You have this in odd number of dimensions. You will get that there's no local contribution. You will still always have zero modes that you have to take care of, but you don't have this local contribution. So for black holes in odd number of dimensions, then it's even easier to compute this. Okay, so it's very, very simple. So what I wanted to do next, to close this part, because there's another third part that we have to discuss, I want to tell you, before we move on to the puzzles that we had from the first lecture, I wanted to discuss some patterns that we see on the C local. So you might say, great, you can compute another thing in this entropy. Who cares? Because I still don't know what quantum gravity is. But okay, but this is where you have to start being observant and seeing, what do I learn from computing this correction? Okay, so here's something that you will learn. So let's take it slowly. You always have to look for clues on what's going on. And so let me first tell you something interesting that happens for cases where you have zero cosmological constant and you're in 4 dimensions. Okay, so this is basically a working example. And the theory, they're basically the IR EFT that we're going to consider. So basically, where am I going to do this computation? It's going to be a theory that has an Einstein-Hilbert term. Okay, so we'll have one graviton. So when I compute the one loop correction, I have to include the correction that comes from the graviton. And then I'm going to add to it some number of U1 gauge fields and NS number of massless scalars, massless and Dirac fermions, and massless gravitinos, spin 3/2. Okay? And what I wrote down here, this is a computation that was done a few years back. For this arbitrary amount of massless fields that you have listed here, if you grab your favorite black hole in this theory, you can compute what this number, well, what this quantity before will be. So in 4 dimensions, I will have to compute before. And here's the expression of what before is. Okay, so it depends. There's amounts that are contributed from the graviton, and then you can see here the dependence on, like, depending how many scalars, how many vectors, how many fermions, how many N3s you get, and there's terms proportional to the Riemann squared, and then terms proportional to the Ricci scalar. Okay? That looks disgusting. Right, and then you grab your black hole, you compute the Riemann tensor for the black hole, you compute the Ricci scalar for the black hole, you integrate that, and then that will determine for you C local, and then you will say, it's a contribution that comes from that one. Okay? That's disgusting. Very not insightful. Now, there's a nicer way how to write down this before. So instead of writing it in terms of Riemann and Ricci squared, I can trade that in by the Weil squared and the Gauss-Bonnet term. And so a nicer way how to write down before, just so that it's a little bit less disgusting, is basically as a number. So there's going to be a coefficient. You can read it off from all those combinations of coefficients that you have there. So sometimes people like to write it like this, in terms of like a number multiplying Weil squared, and then another number multiplied the Gauss-Bonnet. So this gives you the reason why it's convenient to write it like this, and this basis of Weil and Gauss-Bonnet, it's because of conformal anomalies. Just if this resonates with you. But if not, it doesn't matter. Okay? So, and the label A and C are basically the two conformal anomalies that appear in 4D. Okay? So that's the reason for that. And you're like, okay, great. So that just reorganizes those coefficients there. But then something that is very interesting. So if I pick that matter content, so if the EFT is supergravity, so you basically arrange the number of scalars, of vectors, of fermions, of gravitinos, such that everything falls into a multiplet, into a supergravity multiplet. There's something really interesting, and it's that this, whatever multiplies the Weil squared, is exactly equal to 0. And then A, it still has like a not super insightful formulation, but basically this calligraphic N is the number of supersymmetries that you will have. So it can be n equal 2, n equal 4, n equal 6, n equal 8. This is the number of vector multiplets. So I'm organizing this answer here is organized in terms of n equal 2 multiplets, and these are the hypers. But what's interesting about this is that if C is equal to 0, then B4 is just the Gauss-Bonnet term. And that tells you that then C local is a topological number. Basically, it will not depend, as you do this integral, basically this is independent of black hole parameters. If C is not 0, then you have to integrate the Weyl squared. And the integral of the Weyl squared will depend on the charges that the black hole carries. Yes?
So why C is equal to 0 for any n?
Well, it depends easy. There's a beautiful paper, I will give it in the list of references. It was not obvious. So there's a paper by Finn Larson and Anthony Charles, but it cancels multiplet by multiplet. So that's what they basically show. So the bosonic degrees of freedom in each multiplet cancel the fermionic degrees of freedom of each multiplet. Yeah, that formula there, that's why I wrote it like that as well.
N equal 1, then only...
Oh, but n equal 1 doesn't have black holes. So, because you don't have, well, it doesn't have BPS black holes. So that's why the formula is interesting for n equal 2 and higher, because you need a gauge field. And so only in n equal 2, then the gravity multiplet has like the gravity photon, and then you can have supersymmetric black holes inside of that theory. But at n equal 1, then there's nothing interesting going on from that point of view. So this is kind of interesting. Okay, so if the theory is, and this is also, it's also true that C is equal to 0 just because of the matter content, not because of the black hole being supersymmetric or not, I should say. So even if the black hole is not supersymmetric, C is still equal to 0 because it's something that just depends on the matter content. And then this correction is always topological. So that's kind of curious.
Chiral multiplet doesn't contribute there?
What's that?
Chiral multiplets?
There's no chiral multiplets, or at least in the terminology that I'm using for supergravity. There's only vector and hypermultiplets.
But can A be 0 also?
What's that?
Can A be 0 also?
Yes, it can be 0. So for, well, the whole contribution, you have to be a little bit careful, but, sorry, the total C, there are theories, so if you have n equal 8 supergravity, the total C, if you include the 0 modes, is 0. If you can find numbers of vectors and hypers, like positive integers that make this 0, then yeah, you can play around and see if, yeah, there will be coincidence there. But you still have to account for the 0 mode contribution.
Yes.
So, but yeah, but if in n equal 8 supergravity, when you account for all the contributions, the 0 mode and the local part, the total correction is 0, which is,
Wait.
no, sorry, not n equal 8, sorry, it's n equal 4. In n equal 4 is 0, there's no correction in n equal 4 supergravity, and then in n equal 8 is like -2 or something. Sorry, yeah. So it's kind of, don't ask me, and you would say like, why is n equal 4 0 and not n equal, like, I don't know, it's just a combination of numbers that show up there. So, but then for those supersymmetric cases, this is where you have a counterpart prediction in string theory of what should be the microscopics, and people have matched those numbers. Okay?
Excuse me, those vector multiplets and hypermultiplets, those are the number of vector multiplets?
Yeah, it's how many you have.
Okay.
Yeah. So you just tell me, oh, I have this number of vector multiplets, this number of hypermultiplets, and then it's just an integer. It will just be a number. Because the integral of E4 is just going to be a topological number. So it's just a coefficient that multiplies this complicated things. Okay. that's that. Then a second case, so let's do ADS4. Black holes, okay? So here the cosmological constant is going to be negative. And B4 in this case basically takes the form. So again, it's useful to write it in this way. So there will be some coefficient A and C for the Weyl squared and the Gauss-Bonnet term squared, but then also because of the equations of motions of the theory, you'll also get two additional terms. That are this form. The reason why you don't get these terms up there, it's because if you don't have a cosmological constant, the equations of motions always tell you that the Ricci scalar is 0. So that's why I didn't write them. So even here, this is a little bit of an abuse that R is equal to 0 for a theory that doesn't have a cosmological constant. But then if you have a cosmological constant, then you can get terms that go like R squared and R times F squared. Okay? So these two terms here, then there will be some coefficient that I'm calling beta 1 and beta 2 that are new. So now we can then look at, so this case is more complicated, and the only thing that has been done for these types of black holes is look at minimal supergravity with n equal 2, and of course in this case, it's what we call gauge supergravity. And in this case, so you will compute B4. And the answer is 11 over 24 times C4 minus 13 over 36 R squared plus 13 over 18 R times S squared. Okay? So the coefficient C here is still 0 for the supergravity, but you get now these other two contributions. So let's do an evaluation of this, for instance, for a BPS black hole. So let's consider, in this theory, there's an extremal BPS black hole, which is ADS4 per Newman, where the supersymmetric condition is basically that the mass is equal to the electric charge plus angular momentum over L. And then the way people like to parameterize this, there's a parameter A in the solution. I'm not going to write down the metric and all the properties, but in the final answer, we're going to express it in terms of that little a, and then you will compute C local in this theory. So you will evaluate these quantities for the curvatures and the field strengths associated to the solution, and you get 11 divided by 6 minus 6 over 3 A get some discussion that depends on that little parameter A and the cosmological constant, so this L that's sitting up here. Great, you did a computation, you computed the log that comes from just this ungauged supergravity, and that's what you get. Now, I'm in ADS4, right? So what can we do in ADS4? We can do ADS4 CFT3.
What is this in ABGM?
Not that.
No?
No. So if I would have think that this was all I needed to know about the low energy effective field theory, you will not match ABGM. Which brings me to a really interesting property here. So, so this is a lesson here to basically appreciate and understand about these black holes. Is that, so in known instances of ABS4, CFT3, so basically cases where we know which conformal field theory is dual to some supergravity, the prediction, or well, basically the answer of the C from the CFT3 index is that basically C is independent of black hole parameters. It depends a little bit on like how much supersymmetries you have and precisely what the theory is, but it's basically like integers. It's like 2. So something extremely simple. And so this computation that I did in ABS4, even though I did it in supergravity and I did it for some supersymmetric black hole, it clearly doesn't match the CFT. And so what's going on here? Because there have been papers that if you have, you can search through the archive and people will tell you that for supersymmetric black holes in ABS4, we understand the area law matching and then the logarithmic correction. And so what happens for these known examples is that your low energy theory is not just minimal supergravity. So these examples actually come usually from ABS4 times some 7 manifold. They're compactifications of M theory. Okay, so in the simple case, this M7 is just this, the 7th sphere. Okay, so that's the BGM. Okay, and when we do these computations, as I highlighted up there, you have to include all of the light fields that you have. And the scale that is determining the size of the black hole in this situation is the ADS scale. So L here is the thing that is telling me how big the black hole is, and it's going to tell me what are the light fields that I have. And so of course there will be the light fields that come from this ABS4 part, but then this guy is controlled by some size L, but then the M7, the size of this M7, is also controlled by the same scale L. Okay, so when you look at the solution, this has some size L, this also has some size L, and so the light fields in the situations is what comes from this whole configuration. So you have a whole tower of Kaluza prime modes that are coming because you did a dimensional reduction on M7. But you can also play a different trick. You can say, look, these black holes in these instances of ABS4, CFT3 actually come from 11 dimensions. So you could consider the path integral in 11 dimensions, not go down to 4. 4 is an even number. 11 is an odd number. So from an 11-dimensional point of view, there's no C local. So if you do the computations in 11 dimensions, then C local is equal to 0, and the only thing that you have to compute are the 0 mode contributions, which is kind of some trivial contribution.
can I compactify in S1 and then compactify to the
You can do it. The answer should always be the same because the black hole is what the black hole, like your gravitational theory is what your gravitational theory is. But the thing is that the CFT basically here is telling you that for it to basically, so the thing that I find fascinating about this is that now what I want to do is basically use it in reverse, right? So if the CFT is telling me that this is always independent of the black hole parameters, then it's imposing a restriction on what are the light fields that you're supposed to have. Because a given set of light fields is not going to give you this, even if you had a supersymmetric configuration in mind. So, sorry, what was that question?
The CFT that corresponds to ADS4 is not the same CFT that corresponds to ADS4 with a black hole. So which one is it?
Well, no, but it's the same CFT. It's a state inside of the CFT.
Yeah, it's not a finite deformation of the CFT because you have
No,
change.
it's a state. It's a BPS state. So you compute the index. You look at what are the BPS states in the CFT. But I'm not. You don't have
it's
to.
a finite deformation of that BPS state, right? It's
No.
the
I'm doing
CFT
it
plus,
here. Let's. So this puzzle. So here I'm looking at the extremal BPS black hole.
Right.
But
I agree.
that's just a state inside of the theory.
Don't you have to deform the CFT with this BPS operator and have a new CFT?
But that is still it's
So
an
my-
operation within the theory. It doesn't change the
I
theory.
think is it that when you have magnetic charge?
In this case, I
There
just
is not-
have electric and
Like,
rotation.
I think what he says when you have a magnetic charge, you have to.
Oh, you can
increase-
think, yeah, you have a background field,
Yes.
but it's still fine. I still know what that theory is. There's no like mystery. There's no like, yeah. So it's still something that from the CFT point of view.
I just puzzled by the C is sorry, the C is what's written the fourth edges. What is written there?
Is independent of black hole parameters.
Yes, because the black hole parameters should be related to the BPS operator deforming the CFT.
There's other parts like the entropy will depend on like. I'm not telling you that the entropy is independent of the black hole parameters. I'm just telling you that one correction, one part
Yes.
of
Right.
like
understand.
I still have like the area depends on the black hole parameters. So it's just I'm just highlighting that the coefficient that multiplies the log
Yes. Now
it's independent of the black hole parameters. That's all. Like so it's not the whole. Of course, the entropy of the system will depend on like the parameters that you have. So, but the thing that is cool is that this kind of like correction that you would have thought that okay, it looks super technical what I'm doing. It's actually quite insightful from this point of view. So now you can, like, in some sense, this is a way how black holes can tell you about their UV completion. They're not idiots. So there's something here to predict, in a sense. So I should say that this observation, so this is an observation, let me just be clear, it's an observation based on examples. One thing that I'm obsessed about, I've been trying to see if I can prove that, for instance, if I could prove that this is something universal from a CFT point of view, then it would really give me an extremely strong constraint on what are possible gravitational theories. But still, it's basically telling me this quantity, this statement here, if I take it seriously, so let me just put here not proven. But if true, it imposes non-trivial restrictions on the light fields in my theory of gravity. So this will basically, if you like the words of the swampland, this could be a way how you can distinguish theories that belong to the swampland versus theories that don't belong to the swampland. Basically, theories that could have a UV completion versus theories that don't have a UV completion. Okay.
Someone has tried to compute the light field from reducing the S7, for instance.
Yeah, there's a
Specifically
paper.
check-
So they only did it. So you can also do these log corrections when you don't have a black hole, when you just have like global ADS, and then you're just looking at like like at the partition function on S3 in ABGM, like so just the free energy on S3. And so there's a paper by the group in Leuven, so Nikolai Pavev and collaborators. They grabbed here, they put just global ADS times M7, and they did do the reduction. They still found, there's something subtle because this gives you an infinite tower of fields. So as an EFT, you still have to be a bit careful because there's not like finite number of light fields, there's infinitely many of them. And they were trying to reproduce this, and they kind of, like there was some like -1 or -2, they were off by like an integer, and they don't understand why they were getting it off. I'm pretty sure they have a mistake. They clearly have a mistake somewhere in their computation. There's some order of limits that they're not doing correctly. But yeah, there's been some attempts to say, dimensionally reduce all of this, and then.
Because also I would expect that the light spectrum will depend on what manifold I pick up, but
Yeah.
that also is telling me that it doesn't.
Well, from the 11-dimensional point of view, yeah. If you're in M theory, then yeah. But it will basically, so that's why it's kind of interesting, right? Because it's just telling you, like, of course, an easy way how to get something that gives you C local equal to 0 is to glue something here that is odd dimensional, and then you're going to get 0. But like, yeah, from the 4D point of view, like, can you start seeing hints of that? Like, what were the specific requirements? Because then, basically, if this thing is true, then it will tell me that you can never have, there's no consistent instance of ADS CFT where you don't have large extra dimensions. So this rules out instances of ADS CFT where you have scale separation, which is something that people are trying to prove by solving supergravity.
Do you mean scale separation between the different radius between these two?
Yeah, so scale separation would have meant that this M7 is controlled by a size that is not the same as the ADS 4 size.
So here, the logical view will be to be C local equal to 0 in the IDS 4 black hole, and you will be able to use holography because of this.
Yeah.
That will be
Or well, at least it will be one sufficient.
One way.
Yeah, one sufficient condition for you to say. So you will take this as a sufficient condition for it to be at least possibly matched to a CFT computation.
Yeah, that's.
But like for instance, this thing, I don't know if any CFT that will reproduce that mess.
Yeah, so this is the easy way, and the hard way will be to M7 and M7 to make it so that it compensates DC local. You can do something like that.
Well, that's what I would like to understand. So how do I get rid of this from the point of view of like, including the contributions from these guys? So can I see that the cancellation is happening at some order by order? Like, what is it that I need? And that's not clear. That's an open question. I don't know. I'm asking Felipe and Robinson to help me figure out how that will work. But I find this like super interesting, right? So, and the only thing that we're just doing a gravitational path integral to like one next order. Like, I'm not doing anything more fancy than that. But okay. So that concludes this part of the discussion. Just to inspire you to look at this gravitational path integral in more detail. And what I want to do now is move on to the third topic, because I did present you with 2 puzzles. Oh, sorry, this was chapter 2. I'm now in chapter 3. So now we're going to move on to the near-extremal case. Okay? So let's erase. Please. So what we did, it was all fine, but now I want to do a better job because Breno has been asking me tough questions, and we should do a better job at this, right? So let's look again at this C1 loop, okay? So in the C1 loop, so what we were doing, so let's be clear about this again. So you had a background solution, and then you had fluctuations. We had our gauge field, and so there was a background value of the gauge field, and then we had some little fluctuations for A, and then if you have additional matter fields, and if they have a background configuration, well, it doesn't matter. Usually this part is 0, but then there will be some phi like that, right? And so then the C1 loop, it will have basically, let me be, again, a bit schematic. It will have basically some operator that will depend on this background. And so there will be contributions coming from the metric. There will be contributions coming from the gauge field. There's also mixed terms. There's cross terms between them. And this is a, if you want a differential operator. And then the contribution from the fields. Like this. But the thing that I want to do here, I want to be very careful about this. I want to evaluate this. Let's again evaluate this on the extremal black hole. Okay. So the extremal black hole, the near horizon of the extremal black hole, was basically this quantity. We wrote it like this. So we were looking at the Rice-Nostrum solution. Oh, and I should say, I noticed I had a typo yesterday. It was motivated by one of the questions that you guys asked me. It's not super deep, but I wrote the decoupling limit backwards. I don't know. This is for some reason I switched the position of rho and r because I'm an idiot. So just so you know, the decoupling limit is the original black hole coordinate equal to the horizon plus this rho. It just drives me nuts when I have mistakes that are stupid. But okay, any case. So this is our ADS2 times S2 background, and what I'm going to do, I'm going to write it like this. So I'm going to make a change of coordinates because it's going to be a little bit simpler for the computation. So I just redefined what the radial variable was. So here I have this eta as the radial variable. It's the same geometry, still ADS2 times S2. And I want to look again at this one loop contribution, okay? So let's do this a little bit more carefully, because I have been lying to you. Okay, so let's fix this lie. So what is the lie that I've been telling you? So on this background, we can look at basically this at this schematic part that I'm writing here. So I'm just going to put the subscript 0 to say that it's on the extremal background. So we can look at this operator, okay? And the thing is that this operator, so usually what we were doing is we're saying, let's do a decomposition of this operator in terms of eigenfunctions with certain eigenvalues, right? And then doing the one-loop computation for that. But the thing is that on this background, on this ADS2 times S2, there exist lambda n's that are equal to 0, okay? So there's zero modes to this differential operator. So there's certain configurations that basically, there's certain modes, I'll call them zero here, that have this property, okay? They satisfy also all of your gauge conditions and things, but you can just see, like you look at this differential operator that you will get. It's super long, I'm not going to write it explicitly, it takes about 2 lines. But you will basically see that this thing is equal to 0. How do these things look like? So if you don't trust me, so you can solve for them. These things are really disgusting. So some of the modes because there's actually not one of them, there's an infinite number of them. So you can be super explicit about what the form is. Because it's just to scare you. But you can also just check it if then you go back to the references. So these are modes basically that will have the property that whatever quadratic operator you get from your theory, from your gravitron in this theory, basically they will be 0 modes. Okay. So what's going on here? Okay, I have an infinite. There's a parameter, these epsilons. This is a constant. And so there's basically an infinite tower of 0 modes in this geometry, in this ADS2 type of S2. So these things are actually diffeomorphisms, okay? Because a diffeomorphism, sort of by construction, is a 0 mode of your system. It's something that trivially satisfies your linearized equations. So when you're doing linearized gravity, diffeomorphism is just a lead derivative of the metric. It's just, well, in Einstein's equations, a diffeomorphism is a trivial solution. Like it's not a solution. But yeah, it's just, it, of course, it satisfies the equations of motions, and so that's basically what's going on here. Okay, and so the diffeo actually, so this is a diffeo, meaning that you can write H0 as the lead derivative along some vector of your background metric. And this vector that you would use, I'll only write it, I'm not going, you can write it exactly. You can write exactly the diffeomorphism. Oh, sorry, I put here rho. This is eta. Apologies. It's this radial variable that I'm using here. And so this vector that actually creates this perturbation here, it's at large values of eta, it's basically that diffeomorphism. Okay? So you're doing a diffeomorphism, sorry, you're doing a diffeomorphism along this direction where this function is basically parametrized by the same epsilon n parameter here. And that gives you this effect on the metric, and it's basically that 0 mode there. And there's infinitely many of them. Now notice this integer that parameterizes this diffeomorphism has the restriction that n is greater or equal than 2. So any guesses what happens for n equal to 0, 1, and minus 1? So if 3 values of n, then I'm not taking it into account. The killing factor. SL2R. So for those 3 values of n, you don't have a change in the metric. It's an isometry of the ADS2. But for the other values of n, you will have a change of, it's still a diffeomorphism that is creating this, and this is the effect of the metric.
So these diffeomorphisms are the last diffeomorphisms, right?
Yes. Well, we call them, okay, let's, I know where you're going, yes. But let me not call them large right now, okay? So let me be, they're just, from the point of view of me computing this path integral, these are solutions to box of this operator equal to 0, okay? And yeah, if you want, so these diffeos, basically what they're doing, if you're familiar with the story in ADS3, it's very similar to that. Basically, they're reparametrizing time and doing a shift in your radial variable. Okay, that's what these diffeos are. So that's why they're boundary reparametrizations they're reparametrizations of the boundary time. Okay, good. So in principle, when I was computing C1 loop, so if we go back here, okay, so then when I'm doing my computation of the gravitational path integral, I will have, as a contribution to it, if I was careful, I would have had an integral over all the possible functions that I can pick here. Okay, so over all the epsilon n's that I can have here. And this integral, so basically these two things, what this is what people call diff S1 mod SL2R. So basically I have to do this integral over diff S1 mod SL2R. They don't have any action associated to them because their eigenvalues are 0. So then I don't have, of course, up here any contribution. I have to do this integral. This is infinite. Okay? You have infinitely many of these modes. So intuitively you see. Sure. Okay. So I've been basically computing infinity for you. Well, I looked at what multiplied infinity. But it wasn't infinity. Okay, so we have a problem. Do we? No? We're good? You guys like infinity? You're fine? Maybe. If that's the case, yeah, we can stop right here, clap, lecture over. Is that someone upset about this?
We shouldn't divide by the volume of the group or the diff, like 5 above all of that?
I don't know. I already gauge fixed my path integral. So yeah, you might, basically the point is like, how do I regulate this, right? Because I don't want to claim that the thing is infinite, right? So we should be able to understand how to regulate this. That's basic, but I don't want to just be like, I divide by this thing. Because it is infinite, and so it's like, you should have like you should have some understanding of what's going on. And so, but again, are we upset? Because otherwise I'm also happy to just end here.
It is weird because we are counting microstates, right? It cannot go to infinity, or is it something?
I don't like infinities. As a physicist, this is something that, I know that after you take QFT, that you kind of like normalize them. But I am really hoping that you guys are upset, and I don't see any faces of upsetness right now. You're mostly like, oh, when is lunchtime? I'm hungry. Okay, so are we upset?
Yes.
Okay, thank you. Yes. Okay. Because I'm also hungry, so I need to feel like motivated by, like, give me reasons to finish this story. Okay? Okay, so we want to regularize this divergence. Okay, so we want to understand like what do we do with this? Okay, so if a computation gives you infinity as an answer, you do have to inspect it. It's not like I just divide by this thing, carry on with life. Okay, so we do need to understand how to regularize this. Okay, so how do we regularize this infinity? So the thing that this is our result from only a few years ago. It's a very, very recent result. So this does not go back to the 70s to give us something. This is like 2021. Okay, 3 years ago, people realized what to do about this divergence. So the way that you regularize this, what we're going to do, we're going to say, look, what I want to do is use temperature as a regulator. Because at least intuitively what's happening, this is coming from this ADS2 part that was a temperature equal to 0 configuration, right? And I had this enhanced symmetries at t equal to 0. So let me turn on the temperature, okay? If I turn on the temperature, you would have thought, namely, maybe these things will disappear. So let me define, so what I want to do is define the path integral for the extremal black hole, basically as a limit, as I take t equal to 0, of the path integral of the black hole at some finite temperature. Okay? This is morally what we want to do. And the punchline of what's going to happen, so what I'm going to tell you, is that this is not going to be equal to the path integral of ADS2 times S2. So what Robinson suggested of just dividing by it and move on with life is going to be wrong. Okay? This is what we're going to discover. So let's do this. Okay, so how do we do this? So let's implement. Let's implement this idea. So what we're going to do, so here we have, so for every field that you have, what I want to do, I don't have to increase the temperature arbitrarily high. I can just go a little bit away from extremality. So that's why this part is called near-extremal. So what I'm going to do is that I'm going to look this G0. I'm going to take it to be the extremal part, okay, so the ADS2 times S2. And then the first correction that I get as a solution, as a classical solution, you can see what is the first correction that you get because you increased a bit the temperature of the black hole. Okay? So this you can view it from the point of view of the decoupling limit as the next correction that you get as a function of lambda. Okay? So this is how I'm going to view now. My background is not going to be exactly ADS2 times S2. It's going to be this plus the deformation that comes from the temperature. And then the perturbations, I'm basically going to have the fluctuations that I had on the ADS2 background. And then there will be corrections. If I turn on the temperature, there will be corrections to these fluctuations. Okay, so that we'll call delta H. And you do this for each field. So right now, in our simple example, we just have as a background the metric and the gauge field, but capital A and little a, and so for the little a, you do exactly the same thing. So the gauge field also will be the gauge field at extremality plus a delta A0 at t, and then the fluctuations. You do it for, if you want, you're doing it this, there will be this plus the delta A. Okay? So we're going to do that. Okay, good. So now let's look back again at our differential operators. So the thing that we were solving is that equation up there. So we had basically that you have box on some background, G0, A0, acting on H equal to some eigenvalue times Hn, right? So we're going to implement basically this decomposition that I have here. So on this side of the equation, I'm basically going to write, okay, so we'll have the background differential operator that you would have gotten if you had the extremal solution. And then there will be a correction, a first correction to this differential operator due to the temperature. So I'll call that delta box, okay? And then the Hn, there will be its zeroth order plus delta Hn. And then on this other side of the equation, I will have the eigenvalues at zeroth order plus corrections to the eigenvalues. And then again, the same thing, Hn0 plus delta Hn. Okay? Now we're doing this only to leading order and the temperature. So I'm doing a small deformation and I want to see what is the first correction. So we'll expand this equation to first order. Now, of course, box on H0. So, well, let's write it down. Okay, so we'll have the box 0. So that's this guy times Hn0. And then you're going to have box 0 acting on delta Hn. And then you will have the change of the box acting on Hn0. And then I'm ignoring anything quadratic in the change. And then you have lambda n0 times H0 plus delta lambda n Hn0, and then plus lambda n0 times delta Hn. Okay? To leading order. Now, this, of course, cancels this by definition. And what I can do now, so then my resulting equation is just this side of this equation equal to this. And so then what I'm going to do, this H, I'm going to multiply by Hn0 this equation and integrate over them. Because there's the Hn0s basically satisfy that they're integral over the background manifold. I'm assuming that you have normalized each of them, so I'll use orthogonality of the modes. And then if you do that, you can see, so basically, so I'll multiply this equation by this Hn0. And so for instance, in this term here, so I'll have Hn0 times this multiplied against, or maybe let me do it, how should I do it? Okay, so this term here will give me again lambda n0. That's going to cancel again that one. And then what I'm going to get is just these two terms left over. And so basically, sorry, the correction to the eigenvalue is just going to be the integral of this it's basically the correction to my eigenvalue is basically going to be the correction to the differential operator times Hn. This is very similar, like in quantum mechanics, when you do perturbation theory and you want to see what the corrections to the Hamiltonian are. It's exactly the same. And when you add an interaction term to a Hamiltonian, what is the correction to the eigenvalues of that Hamiltonian? It's basically the same expression. So
I have a recent question. Why the difference of an eigenvector has to be still an eigenvector?
No, I'm not using that.
Ah,
So when you multiply, so in this term,
uh-huh.
what I'm doing, so you have hn 0 times the box 0 delta hn.
And then you act into the other side. Okay, yeah.
Yeah.
Okay, yeah.
And so that gives me
Yeah.
a lambda 0,
Right.
and then
Yes.
yeah. So because it's an integral, you
Yeah.
kind of like you can integrate.
Yeah,
both parts.
you're taking some bracket.
Exactly.
And then you basically factor out the difference in the eigenvector.
Exactly.
Yeah.
Yes. Yeah.
Okay, thanks. Sorry.
Yeah. That's why I was hesitating to do that step. But yeah, thank you. So yeah. So that's all that's going on. And so then you get like this really nice expression for what the correction is to the eigenvalues. And here I haven't used. This is general. I did not have to assume that the eigenvalue, the original eigenvalue was 0 or not. This is basically the correction to any of the eigenvalues as you increase the time. Okay? So now, with this, so now if I compute log of C1 loop, or let me write it just as C1 loop. No, let me write it as log, sorry. So what's going on now here is that now my one loop path integral basically gets corrected. Each of the eigenvalues gets corrected by a bit, right? So what can we learn from this formula? Well, you can see that if the original eigenvalue was not 0, this doesn't do, it's a correction. The eigenvalues are going to get corrected. But what you will see in this case is that if you did not have a 0 mode, then the correction is basically polynomially suppressed in the log of the partition function. Okay, so you will just expand this out, expand out the log, and then you will get some correction to it. But now, if the eigenvalue was 0, this is a huge effect. Because what's happening now, basically, think about it from the point of view of C1 loop. I'm basically doing an integral of these. So let me call these guys there, so the H0s. It's different from the, I'm not referring to this thing, I'm referring to those guys over there. The H0s there, before they didn't have any action. There was no contribution to their action. But now, if they get corrected, they will be corrected by this delta lambda n, right here, times their inner product. So these are, I should also say, sorry, I forgot to mention that. These are normalizable diffeomorphisms. So their integral, this inner product between them is actually, you can normalize it to 1. And this thing here, so if in this whole discussion, the correction to the eigenvalue should go basically linearly with the temperature because it's the first deformation that I'm doing away from the temperature. So whatever you get here, this thing is proportional to the temperature of the black hole, so the correction is proportional to the temperature. What would this tell me here? Now I'm doing the integral now of this to the t. That's again a Gaussian integral. And what is going to be the result of that Gaussian integral? Roughly. What?
Determinant.
Even simpler. Before the determinant, right? So if this thing goes like t, then you're going to get something that will look like 1 over square root of t. If the temperature goes to 0, that's huge. Really big. that became humongous.
It's no longer a correction if it's way too big.
Well, it's a leading effect. It's leading even compared to whatever I wrote at tree level in the I0. Because in I0, as I take the temperature to 0, we get the extremal answer plus the linear response in temperature. That's just fine. That's tiny as the temperature is going to 0. But now here, this one loop effect is the dominant effect as the temperature is going to 0. Okay?
This is the volume of the thermal cycle, or something. The S1.
So, what's that?
The volume of the S1, because you have temperature, you have to periodic coordinate condition.
No. This thing is just, this doesn't give you any temperature. This is the integral over the ADS2.
No, but because this is beta, right? The 1 over T.
The correction to the eigenvalue is proportional to temperature. The ADS2 doesn't have a temperature. If you want the periodicity of the Euclidean time is 1 in ADS2. Like that's yeah. There's no temperature in that computation. Yeah. You can add, like, you can say that there's an IR divergence, but yeah. So this is a huge effect. So okay, so let's do a more careful job. So what happens to these corrections? So for these modes, here, this is what people call tensor modes. By the way, how am I doing on time? Am I 20 minutes left? Ah, okay. Are you being kind, or is it
Yes.
true?
Yes. Like 10, but
10? 10 is great. Like I don't. But I want to know if I'm in. I forgot because we started late. I have no idea what time it's supposed to be.
yes, 10 is
10 minutes is okay? Okay. So these things is what people call tensor modes. So then what you do is that then you look at the log, you look at just the contribution that come from these tensor modes. So I don't need to keep track of what everything else is doing as I correct the temperature. You're just looking at what these zero modes are doing because of this argument. So the zero modes are the ones that are really giving you a difference, potentially a difference in the thing. And so, so for these guys, on just this Rn solution, so I'm just stating the result for our favorite black hole, the one that we've been studying all along. This change in lambda n is something that you can compute, so you just evaluate that box equation there, and what that box equation is going to tell you is that this is n pi t divided by 2 over r naught, okay? And so then you compute the log of C tensor. There's a factor of 2 because I'm writing the solution as complex, so I have to take the real and imaginary part. But that's okay. And then this is equal to the log of m pi t. So then you do this product here. In principle, this is an infinite product. So it's actually infinite as well. But this you can do zeta function regularization. And so if you do zeta function regularization, then basically this thing up to some coefficients. So, well, let me I'll write it down. So then this is going to be the log after zeta function regularization of there's factors of pi that are not important. And then I'm going to get t to the 3 halves, and then 2 times r naught to the 3 halves. But then the bottom line of this, because the correction that I'm getting to the path integral, so the log of this tensor part of contribution to the path integral is 3 halves log t. Okay? Now the story doesn't end there. So here what I have shown to you is one type of zero modes. What you have to do then carefully is inspect that every single contribution that I have there, you have to look for zero modes in everything. Okay, so you'll also have actually zero modes to what people call the vector mode. So there's more diffeos that I'm not going to write down because I only have like maybe 5 minutes left by now. There's also zero modes in the gauge field. So you have to collect every single zero mode contribution that you get. And so in the case of Rn, so then for Rn, we have what people call tensor modes and vector modes. Each of them actually have the same contribution. So then when you look at the log of set one loop, Near-Extremal, the temperature contribution that is important is basically you get 3 halves log t from the tensor modes and 3 halves log t from the vector modes. So in total, you get 3 times log t. Okay? So what do we do with this? So now let's revisit thermodynamics. So I did a better job at computing my path integral. So what am I getting from my path integral? What I'm getting from my path integral near extremality, I'm getting that my path integral is going like t to the power of 3 times this I0 that I had from the tree level part, where here, let me schematically write it as like, I get the I0 that I got from extremality, and then I would get a linear response in temperature times some prefactor, like an I1 that comes from like the deformation. There's a number there that I won't care about. It's basically this mass gap that we were getting, but you basically will get this correction in T. So let me not even write a coefficient. This is schematic, so you will get something like this. Okay? So a better estimate for what our path integral is near extremality is this. Okay? So now if I compute the energy, I will get whatever I get classically, basically what will come from the exponent up there, plus now a linear correction of temperature. And then for the entropy, we can also compute the entropy. So the entropy, now I'll just write it, but it is a little bit weird. To interpret, you will get basically the classical contribution to the entropy times 3 times log t. Okay? This is what you will get for the entropy. Now, instead of the entropy, let me consider the density of states. So this will be e to the beta e times that B of gravity. Okay? So of course this is e to the entropy of the black hole, but let's compute this. And this thing, so when you input that this is the form of your gravitational path integral, you're going to find now that this thing at low temperature goes like energy squared. So what is this telling me? And this is the energy, just to be clear, this would be the energy. So here, this E is the energy above extremality. Okay, so you always have like the background mass of the black hole, but this is basically how much energy you get on top of it. And what this is telling me is that as the energy goes to zero, the density of states goes to zero. So if I plot rho of E as a function of E, this basically will have some form as you complete it, but basically now it's going to zero. What did we have the previous time? If I only had the classical contribution, if I was only looking at the area law, this was the part that we were confused about. The classical contribution will basically have told us, no, you have a density of states. You have some amount of finite entropy. This residual, this first puzzle that I gave you, there's a huge amount of residual entropy. No, there's not. That's coming from this part here, because we thought that that was the most important effect. This is the most important effect as you go to low temperatures and low energies. So the conclusion here is that extremal black holes have no entropy. Their density of states goes to zero as the energy goes to zero. And it's because of quantum correction that you're incorporating into the system.
So, in the paper of Stanford, they give the square root of E.
Yeah, that's because they only have the Schwarzschild part.
Ah.
But then I have, so there's like there's two cinches.
Ah. Okay.
No, it's not square root. I think it's.
In the limit. Well, it's a cinch of a square root or something like that.
Yeah, but be careful here because I do have more contributions, so there's more zero modes and stuff. But I thought it was cinch of E, not cinch of square root.
Maybe cinch of E. I know that they made it like the square root of E near the.
Okay, but this is what I'm getting from like all the zero modes. So that's why when you do it from a higher dimensional point of view, that's why you have additional zero modes than if you're just doing a 2D model of JT. Okay, so just from like for instance, this is the part that is coming from SL2R, but then you have a part coming from SU2, from the 2 sphere. That's what these vector modes are. So black holes, extremal black holes have no entropy. We've been lying to you all along. And it also resolves the other puzzle, because now there's a linear correction in the temperature, so yeah, these guys can emit Hawking quanta if they want, they can do whatever they want. But basically there's no entropy at extremality. Now, so this is the picture that you will get if the black hole is non-BTS. If you then do the same computation for a supersymmetric black hole that I don't have time to go through, but just to tell you, if you do this computation for a BTS black hole, there are additional zero modes because you have fermionic zero modes that you have to take into account. And so then, but again, it's the same philosophy. You're not changing the rules. There's going to be zero modes from the metric and from all the parts, but then the fermionic ones are going to cancel against the supersymmetric ones.
You have the Gaussian integral with the inverse power of temperature.
Yeah, if you want, like the determinants are upstairs and downstairs if you want. Yeah, yes. And so if the black hole is BPS, then you can see that basically what happens is something like this. and then what you expected classically, the orange line is what you were expecting classically, something like that, and then this is the gap. You can estimate. Basically, it's the gap that you would have thought that you had from the classical analysis. Okay. So in a supersymmetric case, you do this gravitational path integral, and you will still see that this temperature dependence does go, this quantum correction does go away because of the fermionic and the bosonic degrees of freedom. But if your black hole is not supersymmetric, then the bosonic degrees of freedom are basically going to tell you you're going to see. Okay? So what is the lesson here? Don't just stay at tree level. Explore things at one loop. There's a really interesting thing that a gravitational path integral can teach you. Okay? There's quite a lot of information in it. There's intricacies there. Usually we don't, like historically the reason why it's ignored is because they told you that this theory is not renormalizable. And it's like, don't do loops. Because who knows, you're like, nothing makes sense, there's no prediction. That's the wrong attitude. It's a very old-fashioned attitude. There is information in doing these quantum corrections. There is valuable, robust information that we can get. And this type of examples are illustrating this, okay? There's more to learn about it. So with that, I'm done. Sorry that I went way over time. But time for lunch. Thank you.
What do you expect will happen with astrophysical black holes? I mean, because okay, here you're considering non-BPS but near-extremal black holes, and you show this sort of like a very robust behavior that if you take into account the one-loop correction, actually the density of states go to zero and so on. So what do you expect will happen with astrophysical black holes? So
there are some papers, the group in Harvard computed it for near-extreme care, and you get basically the same thing. No, I don't know, like if there's a, look, these temperatures are still super tiny. So if I put numbers, this temperature is like 10 to the minus 20 Kelvin. So I don't see like a, it's more conceptually about how do you interpret a quantum extremal black hole. And so
right.
the lesson will be that the extreme care should not have an entropy associated to it. Because and its path integral will have the same problem. It also goes like 3 log t.
Yeah, so but basically, can you see how this scales with the spin parameter? I'm saying because even astrophysical black holes sometimes have like spin parameter, I don't know, 0.999 or something like that.
Yeah.
I mean, sure, like there is always an infinite difference between something that is extremal and something that is near-extremal. But the astrophysical like here black holes are very, very fast rotating.
Yeah, and their gravitational path integral, like everything, of course I just did Weisser-Nordstrom because there's spherical symmetry and it's easier to write these things. But every computation that I've done, you can also do it for the astrophysical black holes. And the prediction is that their gravitational path integral basically has exactly
the same feature.
Yes, it's the same.
So the making the extremality instead of with Weisser-Nordstrom mixing charge and mass, if you do it with angular momentum, everything
goes through. It's just way more tedious constructing these zero modes. It takes a little bit longer work.
Like what are because the large diffeomorphism will be different. But
they're like you have to kind of correct a little bit these equations to accommodate for the fact that they're rotating.
Right.
But like it just goes through.
So maybe actually it is true that black holes have closer to zero entropy instead of
yes.
Like real ones. Okay. Thank you. Sorry for asking this, but because this is really, really surprising and really non-standard.
I grew up with people telling me like there's black hole entropy.
Yeah, they're like the most the most entropic objects in the universe.
At finite
this black hole
temperature
information paradox and so on.
But at finite temperature, they will still have a huge amount of entropy.
Right.
So just this curve is going to zero near here.
Sure. Yeah. So
It do have still a lot of entropy inside of them.
Yeah.
If they're hot.
Okay. Right.
But it's just as the temperature goes to zero,
the behavior.
The entropy is going to zero, which is compatible with the third law.
Right. Thank you very much.
When you talk about ADS4 and on 11-dimensional supergravity.
Yeah.
But what happened with ADS5 process 5? Because you don't have C local there, but you will have.
Yeah, so people cheat, right? Because then you just stay in ADS5.
Yes. And you have to fix the C local in the 10-dimensional space.
Nobody has done that computation. I find it super interesting because you would think, but I'm in 5D, C local is 0. But then why is it in 10D?
It seems like you have to fix everything there to have the top-down anography.
Yeah, exactly.
Or something like that.
Yeah.
Also,
But nobody has dared to do that computation in 10D.
but you can do something like the Strominger buffer counting and maybe do the.
No, this is a gravitational computation. Well, then you can look at n equal 4 civarian mills and get the log correction from the index of n equal 4 on S3 times S1. And people, they know how to get the leading part. Extracting the log corrections from the index, I don't know if someone has been able to read them off. Because these indices are very complicated and stuff. But in principle, there's an answer. I think yeah. There's probably in one of these papers that the answer is reported, like it's there, but people have not emphasized on it. But in principle, yeah, the problem with ADS5 black holes are BPS. If you really wanted to do the honest computation, they're also super, like they have like 2 rotational parameters, like 3 charges, and there's like all this like stuff going on. So, but nobody has done that. Like carefully say, let me do the computation in 5D, let me do the computation in 10D, see that like things are okay. No.
Also, this is like a factorization of 2 path integrals, a shaky path integral and not a path integral.
Yeah, if you want, that's what I'm doing here. Like, there's various contributions.
Yeah.
So I'm just singling out, like every contribution is multiplying each other, right?
Yeah.
And so you're just focusing on different contributions. So for the log A, it's mostly like the parts that are coming just from like the non-zero modes and the basic like zero mode. There's different zero modes that are coming from killing symmetries. So those you can deal with. But then it's multiplied by this other effect from these other non-zero modes that give you this temperature behavior. But again, if it is supersymmetric, then this thing, then you can play Robinson's game and be like, nah. But the lesson of this, yeah, the reason why that was because of supersymmetry, because you were having a canceling of divergences. But if it's not supersymmetric, if the extremal black hole is not supersymmetric, then that was a terrible thing to do and you missed this important effect. Yeah.
Okay, so we thank again Professor Castro.